The end behavior of graphs of polynomials. Suppose f is a polynomial function with a leading term of a times x to the n power where a is not equal to 0 and n is a natural number, so that just means positive whole number. And then the end behavior of the graph matches one of the following. Okay, and I kind of have terms for these that I like to use that is just kind of a quick way of describing it, okay? For a is greater than 0, so if a is a positive number, so that's our leading coefficient is positive. And n is an even number, so that would tell us that our degree is even, right? Degree is even, like 2 or 4 or 6, etc. Then as x goes to the far left side of the graph, y goes up. And as x goes to the far right side of the graph, y goes up. So on the left side of our graph, y is going up, and on the right side of our graph, y is going up. Sometimes I call this up and up. Just a quick way of describing it. The ends of the graph are both going up if it has these characteristics, okay? Let's look at a quick example. We actually kind of already saw this a little bit today when we were doing the intermediate value theorem. So this particular one, if I factor it, oh, well, it's ugly if I factor it. So if I factor, so let's not do factored form, let's just do transformation. What does this minus 2 mean on our graph for the transformation that we learned about last week? Yes, I'm asking a question. Try to answer it for me if you can. Down 2, perfect. So we take our parabola and we move it down 2. So on to, I cannot draw graph nice curves with my computer today. That's not bad. Okay, so we have a nice parabola that's down 2. The important thing is the leading coefficient on this one. Leading coefficient is 1. What's the degree? The highest exponent is 2. So the leading coefficient is positive. The degree is even, and the ends of the graph are going up. That's what we call end behavior. Let's look at the next one. For a is greater than 0, so the leading coefficient is positive, and n is an odd number, so the degree is like 1 or 3 or 5, etc. Then as x goes to the left, y goes down. Those negative infinities, right? And as x goes to the right, y goes up. So we call this end behavior down, up, because the first end of the graph is going down, so left and down, both x and y are negative, and the right side of the graph is going up, both x and y are positive. Okay, let's look at an example of this one. I think we already saw this particular problem earlier today as well. So we have x minus 2 times x plus 3 squared. And that means that our leading term is x cubed. And so our leading coefficient is positive. And our degree is odd. So the end behavior should be down, up. Let's look what that graph will look like. All right, so we have our point at -3 has a multiplicity of 2, and then we have a point at 2. I'm just going for my factors and zeros. So if the end behavior is down, up, I could also multiply out the constant term, the y-intercept. I think we did this problem earlier. It was a -18. and we discovered that this graph looked something like this. And this end of the graph was going down and this end of the graph was going up. I started telling you that that was because of these details, but then we plotted in points to verify it. So that was already part of our examples today. Okay, next. If a is less than 0, so that means it's negative, and n is an even number, so the degree is 2, 4, 6, etc. Then we have a parabola that's been turned upside down, right? So as x goes to the left, y goes down, and as x goes to the right, y goes down. It's reflected over the x-axis. So that doesn't just apply to parabolas, it also applies to other powers that are even, just like parabolas are squared, other powers that are even. So here's an example of one that would do that. I'm just writing one down. Y equals negative 2x to the 4th plus 4x minus 2. You could use decimals to verify this if you wanted to. I'm just going to quickly get through it. If you were to factor this, you would discover that there's a 0 with multiplicity 2 at negative 1 and a 0 with multiplicity 2 at positive 1. And the leading negative 2, so there's our leading coefficient, is negative, and our degree is even. And so the ends of the graph are both going down. Something like this. And then last but not least, for for leading coefficient less than 0, so that's negative. And n is an odd number, so our degree is 3, 1, 5, etc. As x goes negative, y goes positive. And as x goes positive, y goes negative. It's in reverse. It's the opposite. It's taking a graph like this that normally is negative, negative to positive, positive, and it's turning it upside down, reflecting it over the y-axis. So here's a quick example of this one. We'll just take an x cubed graph, which is my favorite in our math disco. And we've got one side up and one side down. It's been stretched by a factor of 4, but the negative is the important part because it's also been flipped. So instead of it going from down, down to up, up, it starts up, up, and goes down, down. So here would be our x cubed graph, but it's skinny because it's stretched to be more skinny in appearance, but reflective. Okay, so that has our leading coefficient of negative 4 and our degree of 3. So all polynomials will follow these rules. This is another tool just to help you graph them correctly. Let's look at example 5. Sketch a graph of f of x equals x cubed times 2 minus x times x plus 3 squared using end behavior and multiplicities. So let's start by finding the x intercepts. So for x cubed, we have 0. And for 2 minus x, that one's a little weird. Set it equal to 0 like you normally would. Solve it for x. So 2 equals x, even though it's a little backwards there. So 2 equals x, so that would be an x-intercept at 2. And then this last one would be an x-intercept at negative 3. So then our multiplicities for each one would be 3 for the 0, so it crosses there. It would be 1 for the 2, so it crosses there. But then it would be 2 for the negative 3, so that's going to touch our x-axis at that point. Determine the end behavior from the degree and the leading coefficient. So let's multiply all of these. Here's where it gets tricky. You know, when we were finding the leading coefficient, we were multiplying all of the leading terms together when we found that leading term. This time, however, this one's written kind of backwards. So if you want, rewrite it in this order so you don't mess something up. So for your leading term, you're going to multiply those together with the exponents and everything. So we'll have x cubed times a negative x times 3, not the 3, the x. Oh man, undid way more than I wanted to. And then times x squared. So we have x cubed times x is x to the 4th, times x squared is x to the 6th. But because of this part right here, it's a negative leading term. So negative x to the 6th, yeah, perfect, thank you. And that tells us the end behavior. What's the end behavior going to be if it's a negative leading coefficient with an even exponent? What's our end behavior going to be? If you determined that it's going to be down and down because you've got a negative leading coefficient and an even exponent, you are correct. Sketch a smooth curve that results from all of the above. The only thing I didn't have you do for this is to find the y-intercept. So the y-intercept would be like 3 squared, which is 9 times 2, so it's 18 again, if we care about graphing that correctly. But I don't know if that always matters when we just want the basic look of the graph. Okay, so let's do our point at 0. And it's going to cross that point, and our point at 2, it's going to cross through that point, and our point at negative 3 where it's going to touch. And our end behavior is down, down, so we need to be just bouncing up and touching here. And then, uh-oh. What did I do wrong? Oh, I know what I did wrong. I want to point this out in case this ever were to happen to you. Doesn't x cubed mean x minus 0 cubed? Isn't that another way of writing that first factor as x minus 0 cubed? And that's why, our 0 is at 0. So the reason this suddenly threw me off is I was suddenly thinking, oh, I need an... Okay, let me put those back. I was suddenly thinking I needed a y-intercept at negative 18 because I wasn't thinking right. This actually is going to go through 0. If you have an x-intercept at 0, you also have a y-intercept at 0. So it's going to cross through at 0, and it's going to cross through at 2. I don't care exactly right now where this point is or that point is. All I care is that it turns. If you look at Desmos, you're probably going to discover that one of these is taller than what I've scaled it here. I don't care if your scaling for your minimums and maximums is 100% accurate. What I care about is your end behavior, your zeros, and that you've got turns in there to get your points going through the zeros at the right places. All right.